I turned the music down. I turned you down too, which is not what I meant to do. Okay, let me raise that up. All right, try that again, Ashanti. I think it was you.
Is there a way that we can turn the relative dating lab in this weekend?
Yeah.
Because I've not finished up yet.
Yeah. Go ahead, submit it this weekend. It's all right. No problem.
Okay, thank you.
Yeah. Did you have questions about it? You just haven't gotten to it yet.
Well, I started it, but like some of them I was a little confused on it, but I made sure I read everything that you gave us with it. But
Do you want to look at one of them, or you just want to think about it for a bit?
yeah, I want to sit and think about it.
Okay.
Thank you.
Sure.
I guess we can go over the end part of the lab again.
The very last question?
Yeah, you know where it has the big bar graph?
Yep. Okay, let me get rid of the screen. Okay, let me just pull it up. Get this out of my hand. Dun, dun, dun. Okay. Let me share the screen. Okay. You can see that, right?
Yes.
Okay. So you're talking about this one here. Is that right?
Yes.
Okay. It's got this big table that you're supposed to fill out with a time bracket. Right. So for this one, what I want you to do is first work out the order of events and make sure that you include all of these elements here. I think in the lab version, like some of those showed up beneath the cross section, so don't miss them if they're underneath. There should be one of these items, one bullet point for each of these units. And then, so you can put those in order here from oldest to youngest. And so I don't forget to mention it, after you're done assigning the time bracket to it, then remember that you need to write out an explanation, and don't forget to add in like all of these elements into your written explanation. Okay. So when you have these in order, generally the oldest events are at the bottom of the section of rock. So start out somewhere down here, and then you're going to work your way up to the newest events. Notice that the time is on the side right here, Paleozoic and Cenozoic. So you're not given enough information to actually put like an age in millions of years associated with one of these beds. So what you should do is instead say the early Paleozoic or the middle Paleozoic or the late Paleozoic, the early Cenozoic, the middle Cenozoic, that sort of language, to just talk about the earlier time period. The earlier part of the Paleozoic would be, I don't know, between 525 and 400 million years. And maybe the middle is from 399 to 300 million years, something like that, based on the geologic time scale. But you don't need to assign those numbers, just say early, middle, late. Does that answer your question for that one?
Yes.
Okay, good.
Wait, for the early, middle, late part
Yeah,
is the top one's supposed to be early, right?
the bottom is early.
Oh, okay, okay.
The bottom, okay, so think of it as like if you were talking about this in, if you were looking at these rocks in the field and looking at a cross section, like an outcrop, the bottom would be the oldest stuff. So you would see, you would normally say, like if you were describing the stratigraphic section, you would say the lower Paleozoic, the middle Paleozoic, the upper Paleozoic. But because we're talking about time instead of position, we say early, middle, late. So early is the lower part, middle's middle, and the upper is the late part.
Okay, thank you.
Okay, sure. Oh, it's 10:30. That happened quickly. Okay. I'm going to put this away then. If that's all right, if that's the last question. Are there any question? I guess this is the lab you're, yeah. This is the lab that's due this week. Okay. Let me, so what I want to do is I want to make sure that everybody understands how to install Google Earth on their computers. Has anybody tried that yet? And have you had success? Does anyone need help getting Google Earth installed?
It's been working good for me. I'm actually using it in another class of mine.
Awesome.
I've
Okay.
I've actually installed it on my computer too, but I don't know if it's working just correct even though.
Okay. So have you tried turning it on and it'll open a window and you see the spinning globe and it usually stops spinning on North America.
Yeah, if I can remember correctly, yeah, I think so. Yeah.
Well, you could look at it right now if you want.
All right.
Yeah, go ahead. If you haven't done this, this is a great chance to go ahead and do it. I'll share the screen so that, with iLearn so you can I'll point you to what to do. Okay, so if you haven't done this or if you're unsure, let's go to the lab. So it's lab 5 and it's this 5A that I wanted you to do to get ready for today. So these are just your worksheets. And then I say you've got to download Google Earth. So this link should take you to exactly the right spot. Oh yeah, it just asked me if I want to download it. I've already got it, so I'm not going to click accept and download. But the other link that is also on that page takes you to this page. So all I did was give you a link to this page and a link to this button. So the button you want is Google Earth Pro on desktop. You click that and download Earth Pro on desktop. Should give you the same kind of window. And it should automatically detect what kind of computer you've got. So if you're working on a PC, it should know that and give you the right version. If you haven't done that, do it now. We'll take the time in class to make sure you've got Google Earth going. And then I'll go back here. So the first link, this link gets you to that page. This link takes you directly to the download. And then you also need to download this one, the Geologic Map of California. That's a file that you're going to need to open in Google Earth, and download this one too. So please go ahead and start downloading those things. And I'm going to close this page and I'm going to open Google Earth so that everybody can see what it's supposed to look like. Stop me if I'm going too fast. There, and let me open Google Earth. I guess I don't have a button for it. Okay. Just a second. Mine's opening. Okay. Here's the link. It usually pops up with some kind of tips for Google Earth. This might be a little much for the computer with this spinning ball. I wonder if it's too much. Come on. Well, I guess this gives you a chance to download those files. Could you just, while you're doing that, would you give me, in the participants window, would you just give me a yes or a hands up if you've successfully gotten Google Earth to work on your computer? Good. Handful of people. Okay, I don't know why this is still doing this. I think I'm gonna quit and try again. Okay, let me try that one more time. I'm gonna let it open further before I start sharing the screen. Huh, I wonder if the server is down. Is anybody else getting into Google Earth right now? Thanks for your votes. I'm gonna clear those for the next question. If you could tell me if you guys are stuck with this spinning ball too, or if you're actually getting in.
I'm currently using Google Earth and it's working just fine.
Yeah, okay, so the server's up.
So nice.
It must be me. Oh, you know what it probably is? It's probably because there's 3 of us here in the house all Zooming at the same time. That's probably what it is. So I'm just I'll quit out of this. Sorry that I can't show you. But basically that's the interface that you need. Oh, you know what? I could show you. Oh, it's asking to try to repair. Okay. I'm going to clear. It's giving me a repair window, which is interesting. That's good. Maybe that'll help. I'll try this one more time. I've decided that even with the spinning ball, I could show you a few things. Okay, let me share the Google Earth screen again. Okay, so I'll just show you. Okay, so you can clear that window. That's not part of it. This part is where the globe will show up and you'll zoom into the Earth. Up here in places, this is where when you open the KMZ and the KML file that you just downloaded, those will show up in the places and you'll be able to toggle them on or off. So you click the checkbox to turn it on or click it again to turn it off. Because you don't always want to look at the geology. You don't always want to look at the topography. Sometimes you just want to look at the satellite image. So that's what you'll do there. And in layers, it gives you a bunch of options. And I just want you to turn the topography on so that you can see virtual topography. So it kind of looks like hills where there are hills and it looks like valleys where there are valleys. And to turn off the other stuff that you don't need that's just going to be kind of noisy for your labs. Like you don't need the roads. Well, maybe for not for the lab 5B. For the first part, it asks you to look for a few things, but you get the idea. I give you in the instructions what to do there. But let me just close this because I'm having no joy here. I think it's like what I said. Too many people Zooming right now. My internet is being taxed. Okay. So I am thinking that because this lab has two distinct parts, and because there are a lot of things that you need to download and use and figure out how to do, I need to stretch this out and probably another week, or at least half a week. So, and not only that, but there's no way that I'm going to be able to finish my lecture. And I want you to, this is important enough stuff that I'm going to bump something. I'll shorten the lectures somewhere in some other kind of content instead of bumping plate tectonics. It won't mean that you're missing out on anything exactly, because you'll still have details in your textbook that you'll read. It'll just be the sorts of things that I show you during lecture. Okay, so I'm glad to see that Google Earth is working for you guys. How about those add-ins? Have you successfully, so you need to go into Google Earth, go to the file menu, and then select open and navigate to the KMZ and the KML files and open them from within Google Earth. Or you can right click on or control click on the KMZ and KML files and then choose to open it with Google Earth. And you may need to navigate there to the Google Earth app in order to use it. But has anybody, is everyone having success getting those layers in? Good, at least at least one person. Okay. So if you're having any trouble, like I said in my email last night, hopefully you saw the email. If you haven't, I sent an email at like 9 o'clock last night saying that I would be here early today, that I would stay from 12 to 12:30 to answer questions about Google Earth and to get those layers working in Google Earth. So if you want to stick around and just get that all going, I should be able to demonstrate at that point, or at least like you could share your screens if you're having trouble and I can help you navigate that way. So that,
I have a,
yeah, go ahead.
sorry, I was going to say, I have a question about the pre-lab, but if you can finish what you're saying.
I was just going to say, and tomorrow, Friday, from 11 to 1, I'll be available online to work through whatever you guys want to work through. Like, I don't mind talking about lecture stuff, working on labs, whichever lab it is. Maybe it's the fossil lab, maybe not the fossil lab, the relative dating lab, or maybe it's this plate tectonics lab. But I'm happy to go over any of that during those times. And after we finish up right here, I'll go back to the lecture slides. But go ahead, Kay.
So I have a question on part 1, questions 14 and 15. It's asking about the approximate length of the entire profile, the topographic profile. And it said not a straight line one, that it's, I used the ruler to take into account the elevation for number 14. And then the second one was asking for the straight line distance. Is the straight line distance just the distance that's shown at the bottom of the topographic profile from one side to the other?
Oh boy, that is a question. I am not sure what kind of measurement. You want to share your screen?
Yeah, I can share my screen.
Okay, let's do that. Since I can't log in to Google Earth right now, let's look at yours. Awesome. All right. Let's check it out.
So, I did the measurement here. I don't think I saved it, but doing the measurement with the ruler.
Yes, the
here
bottom, right. Finish your question.
So, doing the measurement with the ruler along here, taking into account the elevation, should that technically be longer than this distance? Is this distance here listed at the bottom, the straight line distance that we should look at?
That is the straight line distance. Yeah. So
Okay.
that's what you want. You don't really, when you're measuring distances, you, unless you're talking about climbing Mount Hood, you don't want to measure all the way up the hill and down the hill again.
Okay,
That would-
because it asks for both.
well, okay. So now you know the difference.
Okay. And should the one that's measured with the ruler over the mountain be longer than the straight line? Because when I measured it over, it was shorter than the one that's displayed here at the bottom of the topo
That doesn't make
profile.
sense. Do you want to try
Yeah,
it
and
again? Can you try just doing another line? Just do one next to it and let's see what it comes up with. Oh, see the ground length. There we go. Map length is as the crow flies distance from point to point. And then the
Mhm.
ground length, I believe, will be if you were walking on the land. So that should be longer. Let's see what you get. It doesn't have to be exact. It can just be,
okay.
yeah. It's almost, that's weird.
But then
It's
if you
barely
look at
giving you
my
any difference.
yeah, because if you look at my topographic profile at the bottom, at the right, it says 12.1 miles.
I think that's your old profile though, because did it just generate a new one, or did you ask it to do that yet? Because you have
No,
to
I
actually
didn't.
click on that line and ask it to generate a new profile, and let's look at that. I think you save and then yeah.
Okay, that one's
Did it give you a new one? I didn't see it change.
It changed and then it went back to the 12.1 miles.
Oh, that's weird. Maybe it's because is it because even you clicked on that line briefly or something. So okay, I think let's work on this after and we'll try it
Okay.
again, and then hopefully I can open mine up and do a different example or something. But that's the way I'm interpreting those two distances, the map distance and the ground distance. I think that's
Okay.
what those mean. But yeah, you're right that it should be longer, because the distance from point to point from the left to the right hand side of that profile should be shorter than if you were to climb up the mountain and then back down, right?
Yeah.
That makes sense. So let's look at that again. Thank you for trying, and you gave a demonstration to everybody on like how to do that in the meantime. Okay, let me get rid of this. Any other questions about any parts of that Lab 5A to get Google Earth started, or can we move on to lecture now, do you think? I will take silence as being a let's move on to lecture. I'm not gonna, I just saw, we only made it through like 24 slides or something the other day on Tuesday. And that was only a third of them. And I put together a lecture that I think I want you to see all of it. So that's why we're gonna just take the time and do it. Let me make sure I've got the right one here. Okay. And I'm not gonna mess around with trying the slideshow this time. I'm just gonna go to what works. Okay, there. Let me shrink this a little bit. And get rid of that. Okay. Okay, we left off. You can see that screen, right? The slides. I'm sharing my screen, aren't I? It looks, it has the, so you should be seeing the age of the seafloor right now.
We see that.
Awesome, thank you. Okay, so we had just, I'll just recap just a tiny bit. We had just finished talking about the age of the seafloor and the magnetic stripes that are parallel on either side of the mid-ocean ridges, and that it grow increasingly older as you move away from the mid-Atlantic, mid-ocean ridges, and that we see this flipping of the magnetic poles in the signature in those basaltic rocks that make up the oceanic crust. And that's what these stripes are. And so we see normal polarity, reverse polarity, flipping on and off as we go out. And it wasn't until we, like, World War II and those years afterwards that we really got to see those magnetic stripes and understand the topography of the ocean floor to put together the idea of plate tectonics. And then we had just looked at this map that shows, and this map doesn't cover every little bit of the ocean floor, because remember, we're taking the sphere and flattening it onto a 2D surface. And so there are going to be some gaps that form when you do that. And that's what these gaps are, is basically that extra space. And so this is the best representation that we've got. And I want you to notice, you're going to be using an image that looks an awful lot like this, but it's got even more detail in your Google Earth Lab in 5B. And notice the legend is it's the age of the seafloor in millions of years, and it goes from 0 at the color code corresponds to what you see at the mid-ocean ridge. And then, I mean, it's like the first almost 10 million years there. And then it goes back in time to the deep purples or blues, depending on what you see, to about 180 million years. One of you volunteered that the reason that the ocean crust isn't any older than that, that it's all less than 200 million years, because they run at some point, that ocean crust runs into a subduction zone, and it's subducted back into the mantle. It's recycled back into the mantle, and that's where that crust is destroyed to kind of balance where we're creating the crust at the mid-ocean ridge. Okay. I put together some slides showing, oh, I didn't mention one other thing before I move on. I just wanted to point out and to remind you that the age of the continents is much older, right? 4.4 billion years old. That's what the G is for giga, you know, gigabytes. This is giga annum, so giga years, billions of years. 4.4 billion years is the age that we have for the continental crust. And that's based on some zircons. I showed you some of those and how we date them using a shrimp that's not so shrimpy from the Canadian Shield. So those rocks were from up here in Canada. So the continents are a lot older than the oceans, the ocean floor anyway. Okay. You're supposed to be seeing pillows here. These are basalts that are on the coast right here, Point Bonita. So Point Bonita is the point that the lighthouse is on that guards the Golden Gate. So if you were to go across the Golden Gate Bridge and turn left and just walk out as far as you could to the west toward the ocean, that's Point Bonita. And you could look out on the Golden Gate Bridge and you could see the other side, you know, San Francisco and all that. So this is what's down there. And I told you that there were oceanic crust rocks and some pieces of mantle rocks that had been scraped onto the edge of the continent when we had subduction happening here. And that was before the San Andreas Fault developed. So the San Andreas Fault is only about 30 million years old. It started at the Gulf of California and zipped its way up California to get to its current point at Cape Mendocino, where it goes offshore and dies off and it merges into the Juan de Fuca subduction, or the Juan de Fuca Ridge and that subduction zone. So the San Andreas didn't pass the latitude of San Francisco until about 10 million years ago. So this happened at some point. It's not going to be recent. It's going to be like millions of years ago, like not even 10 million, like 90 million years ago, probably. This sort of thing was happening, this abduction, the scraping off of the oceanic crust onto the continent. It was happening while the Sierra Nevada was forming. And we're going to get to those processes about how the Sierra Nevada forms. So I'll keep reminding you of these. But what this is, you see all these little rounded blobs. These are pillow basalts. So this is what forms as the basalt is erupted into the seawater. Because when you have this molten rock, it's cooling really fast, so it crusts over really quickly into these black crusty blobs that are very rounded because the pressure of the water that surrounds the lava completely kind of forms it into a ball almost. But it's still molten inside, so it's a goopy ball that kind of can moosh out and spread out. So they're kind of like flattened here. But you can imagine this one being erupted and like a blob of lava coming out. I'm going to show you a video in just a second that explains that. Here's another view. Maybe this is more convincing if you didn't see it in the last one. Here's one. It's surrounded by some other rocks, but it's like there's a little bit of alteration there that just helps to define the pillow. And here's what it might look like if you had a glacier scrape off the rocks across the top of it. That's even harder to imagine as a pillow basalt, I think. But you get the idea that there are these rounded basaltic blobs. This is what they look like underwater. So this is a fairly fresh one on the actual seafloor. And they're just, it was erupted from this side and it sort of splooched over the side there and just gives you this pillow form. Here's a video that hopefully will convince you that this is what I'm talking about. Come on. Great. Okay. Wait. Is it gonna let me? Okay, I guess I have to go find the file.
If you look, it says security warning, references to external media objects
Oh,
have been
thank you,
blocked.
thank you,
If you
thank you.
click enable content, it might work.
Awesome. Good eyes. Your pictures were covering that at the top of the screen. Thanks. Come on. Let's
Maybe not.
it should have. There we go. Come on. So you see this, the steam coming off of it and the black crust that forms almost immediately. So I think that's pretty cool. So now you can really imagine how these things form. Anytime the lava erupts onto a little hill or onto another pillow basalt, it's going to kind of just drip over the side there and stretch those out. But that was taken from a submersible where, it might have been, the easiest place to find something like that would be like an offshore eruption in Hawaii, instead of having to go all the way down to the mid-ocean ridge, which is pretty deep. Some other things that are important features of the seafloor are these hydrothermal vents. And these are tube worms here. So these white crusty tubes and these little red bits that are coming out, those are the worms. These tube worms live on the microscopic nutrients that are in the water here, and particularly at these vents where there are volcanic gases. This is rich in mineral contents, and so hence there's a lot of life around these vents. And so you can have like fairly barren patches of the ocean floor in places, and then come along one of these vents, and then suddenly there's life, there's fishes, there are crustaceans, there are tube worms because of the nutrients there. And then of course any animals that are there attract more animals that feed up the food chain, that go up the food chain. So these are called black smokers also, if you've heard that before maybe. We get pictures of these things by diving in a submersible like Alvin. In fact, Alvin I think there are only 2 or maybe 3 of these vessels. Someone's probably over time there have been more, but I think active at any one time, there are not many of these vessels. And this fits maybe 3 people inside. They're really small. You're sitting crunched up. You can't pee. So you have to hold it, or you got to pee into something while everybody's there next to you. You're down there, you're navigating the submarine, and you can use its attachments to collect samples and obviously to take video, those sorts of things. So this is how you get down into like the Mariana Trench, which is one of the deepest places on Earth, is the deepest place on Earth. They take one of these submersible down. So they can withstand this intense pressure to get to those great depths in those trenches. They've probably been down to over 10,000 feet deep. So it's pretty amazing. This is the ship that carries Alvin. It's the Atlantis, and it's out of Woods Hole, which is in Massachusetts. It's with the WHOI is how you say the abbreviation of it. Woods Hole Oceanographic Institute is who maintains this. But it's something that as a scientist, if you're studying something about the ocean floor, or you might be studying the marine life too, so the biologists are in competition for this vessel, you can sign up, you can make a request to use Alvin, and if your request is a good one, you might get time on the vessel. I haven't been down. I'm not sure I would want to, honestly, because I'm kind of claustrophobic. I would have to get in it and kind of feel it out. I would, if it wasn't too bad, the claustrophobia, I would totally do it, because, oh my God, that's like going to space, but the other direction, right? Okay, so hydrothermal vents. What are these? So these are some more black smokers, more tube worms and all that. And these are just, it crusts over. So this is probably calcite and other minerals that have grown as they deposit it, as they come out of the black smoker, plus anything that's crystallizing from the ocean water, salts and other crystals. So this is hot water. It's kind of like a hot spring on land, but it's under the ocean. they happen near the the spreading ridges, excuse me. They have a lot of metals, iron, magnesium, other metals, and they support life that is chemosynthetic. They actually use the chemicals coming out of the black smokers to live off of. And so there are there are new life forms that have been discovered at these black smokers. And there are economic value to some of the deposits here. Notice right here on this clump of tube worms, this is an instrument that's probably collecting data about, this is an instrument probably off of a submersible like Alvin that is lowered down to collect information about what's coming out of the black smokers so that we can actually measure the chemistry of it. Okay, stop me if there are questions. Okay. Iceland, I told you that Iceland is one of these places where the mid-Atlantic ridge is exposed on land. Iceland is complicated though because there's a hot spot underneath it too. So there is an entire community of people that are pro hotspot and the idea of a mantle plume coming up from the core mantle boundary that we've talked about. So a mantle plume coming up and feeding hotspots. Some people don't believe in those mantle plumes. I do. I think I think they've been imaged well enough that that it's probably correct, that idea. You know, it's still it's still a hypothesis, you know. Is it a theory? Probably we have enough information to say, okay, there are plumes of melt coming from the core mantle boundary, that they make their way up through the mantle and they end up at the base of the lithosphere and sometimes puncture through and actually erupt onto the surface at a hot spot. The con community would probably say, no, it's not a plume that's coming from the core mantle boundary. It's actually melts that are forming in the upper part of the mantle from I don't know what, actually. I don't know how they make that argument. I'm not sure how they argue against the plume, honestly. But there are websites with resources all about the scientific literature that gives evidence for all of these. But there's no doubt that the mid-ocean ridge crosses Iceland. So here's a map of the island. The white parts are glaciers. Iceland is not actually covered in ice. It's fairly green. Greenland is covered with ice, and it's not very green. So if that helps you to remember the two. Not a lot of people live in Greenland as a result of that, but Iceland's a rad place. Okay, so volcanoes are erupting all the time. There was an eruption in, I think it was 2010, that stopped air traffic from across the Atlantic. It stopped air traffic across Europe alone. So the flights just within Europe had to stop for like a week. Transatlantic flights had to stop because there was so much ash coming out of one of these Icelandic eruptions. And I'm not even going to try to say the name of the volcano because it's crazy. And my Icelandic is not the best. What else do I want to say? What this is showing, okay, so this is showing you where the youngest volcanics are. So the mid-Atlantic ridge is coming on shore over here on this side. So if you wanted to go there, you would travel from Reykjavik, where the airport is, and come over to the east side of the island. And do you also see these orange lines with the dots in them. The orange lines are fissures, so rifts where the earth is actually split apart. And so canyons form, and there are volcanic eruptions and volcanoes coming up within those rifts. That's related to the spreading ridge, because the spreading ridge is a divergent plate boundary. Even when it comes on land, it still has the tectonic stresses that are pulling that land apart. And so some of the volcanism on Iceland is going to have a chemical signature of the mid-ocean ridges, and other parts of the lavas that come out in Iceland are probably going to look more like hotspot basalts. They have different chemistries, even though they're both really low in silica. They're both basalts. They're both really low in silica. They're both really high in iron and magnesium. But it's the other elements and some of the trace elements, the ones that are just in, you know, quantities like less than 1% of the chemistry of these basalts will tell us something about its origin. That's also part of the debate. They look at the chemistry of the basalts. In this image, you see, here's the mid-Atlantic ridge. Here's the ridge coming up right there. Here's a transform fault between the two ridges, the two ridge axes there. And then the fracture zone, that scar from the transform fault that goes off to the east. And then there's a scar that goes off to the west. It's that transform just here. And then the mid-ocean ridge continues up like this, and then onto the east side of Iceland. So like right in there. Okay, so that's kind of cool. Most of the tops of those ocean ridges are somewhere about 2,500 meters high. So at like 8,000 foot depth in the, is that right? Wait a minute. Does that seem right? I think that's right. It just seems like really deep water still. I was expecting it to say more like 4,000, but I guess it could be 8,000. I mean, that's what I wrote, so it must be correct. I will double check that just to make sure I'm telling you the truth. That sounds a little deep. That's 8 kilometers, which is kind of like the thickness of the ocean crust, which is why it's making me doubt it a little bit. But the point is that these ridges are mountains on the seafloor. I'll pose the question again. So why do the ridges form where they do? Why is there a ridge at the midpoint at those spreading centers? Remember that the map lady, what's her name?
Marie Tharp.
Tharp, thank you. Marie Tharp. She described in the sketches that she drew, she described these ridges, but she also described a V-shaped notch in the center of those ridges. So the ocean floor comes up to form the ridge, and then there's a V-shaped notch in the middle. That's where the lavas are actually coming out. And the V-shaped notch is, you know, at the center point of these divergent plate stresses. So it's pulling apart. So there's a gap, there's space for the lavas to come up within. And that space and the fact that the plates are pulling apart thins the ocean crust. So the ocean crust is thinner there. That reduces the pressure on the mantle underneath. And just removing some of the pressure off the mantle allows it to melt. So that's all you've got to do is take the pressure off the already very hot mantle. It's probably at 1,400 degrees Celsius or something like that. You remove a little bit of the crust, you decompress the mantle, and it starts to melt. Okay, so how about does anyone want to volunteer why the ridges are there?
Is it because when the lava erupts, it kind of piles up on the outside and makes it more, makes it higher?
That's a good idea. That's probably part of it. There's another more significant factor though.
When there's hot water, it makes the material less dense, so then it starts floating up.
Yes, but instead of hot water, it's hot crust. Exactly. It's the very hot crust of the ocean floor, of those basalts, that means it's less dense than the surrounding ocean floor basalts. So right at the ridge, it takes some time, millions of years, for the entire thickness of that ocean crust to cool, because it's not all erupting into the ocean water where it cools like instantly. You saw it crystallize right away. In that video of the pillow basalts, it crystallizes immediately, but not the insides, right? That was just the outside. So the internal parts of the crust stay hot for a long time, and certainly at depth too, because it gets thin. It's thin right at the mid-ocean ridge, but it gets rapidly thicker. But in those first, and it's probably based on the width and then comparing it to like the age of the ocean crust, those ridges, it's like 10 million years that crust stays fairly hot and buoyant. So that's an important factor in the, remember I said density, and when we talked about isostasy, density is really important to explain plate tectonics. Well, the density of the ocean crust is important too, because it forms the ridges because it's less dense, because it's hot and new crust. But over in these deeper parts of the ocean, right, it gets progressively deeper as you get toward older ocean crust. So this is the area that was like 180 million years in the Pacific. That's deeper. The crust is thinner because it's cooled, and it's become more dense as it cooled. So that crust has already become dense enough that that's what helps it to actually start its dive down the subduction zone. In this case, it's actually oceanic crust up against more oceanic crust in these seas here behind the Japanese islands and the Kuril Islands. The islands are there because it was ocean crust versus ocean crust. I'm using my hands if you want to look at me. If one of them has to win, remember I said when you've got convergent plates, one has to win. It's the one that is less dense that wins, the ones that's more buoyant. So the ocean crust that's colder and denser is the one that subducts. And that's what happens there. This ocean crust is younger and more buoyant, and so it is the one that ends up overriding the subduction zone. And the volcanoes that form because of the subduction actually make up the Japanese islands and the Kamchatka Peninsula and these Kuril Islands, and this whole chain of islands that form the Aleutian Islands in Alaska. Same deal. This is older, denser crust compared to the ocean crust that's to the north of it or to the west of it. Okay. Earthquakes. So in terms of earthquakes, remember we're just focusing on divergent plate boundaries right now. Earthquakes happen while this is taking place. Certainly we have transform faults that are separating these offset segments. Anywhere you've got brittle, like solid crust, not molten or semi-molten, but solid, cooled, crystallized basalts. Anywhere there's friction as these plate moves anywhere the crust breaks, you're going to generate an earthquake. And so in this case, the earthquakes aren't going to happen down here underneath in the mantle, because the mantle's too hot and it's liquid here, and it's too gooey and plastic here. It's going to happen in the crust, well, in the lithosphere. But this is broken by faults. And it's a particular kind of fault called a normal fault. We'll talk about that and more when we get to earthquakes and faults. But it's breaking up as the plates are pulling apart. And you're getting these blocks that kind of just like dominoes kind of like lay in a line, and between each domino is kind of an earthquake, is a fault that can generate earthquakes. So the earthquakes that happen at divergent plate boundaries are shallow and fairly small. And if you look at a map of actual earthquake, these are epicenters. So these are epicenters as opposed to the focus, or the focus of the earthquake would be like the source, like where deep in the earth does it actually start. The epicenter is a point on earth above that focus. And so you just draw a line from the center of the earth to the surface of the earth, and wherever the point on earth is above that earthquake, that's your epicenter. So it's the closest point on the surface from its source. Look at the mid-ocean ridges through Iceland, down the mid-Atlantic, into the Indian Ocean, in the Pacific. They're all red. This scale is depth. So the depth is 0 with red, and it goes down to 50. I think that says 50. Shoot. Yep, 50 kilometers. Or sorry, yeah, 50 kilometers. Orange between 50 and 100 kilometers. And until green, which is between 400 and 700 kilometers. We're way down into the mantle at that point. So you don't get these deep earthquakes associated with mid-ocean ridges. The deep earthquakes have to be associated with a subduction zone. And we'll talk about that soon. So everywhere you see the yellow and the green, that's not one of these spreading centers. So everywhere that you see these red, and it's also the red dots that are also in the ocean floors or in a sea, like here where it's just starting to open up to be a new ocean, that's what I'm talking about. Okay, so a critical point of what I just said is that earthquakes only happen where you have brittle rocks, where you have solid rocks that can break when you deform them. Not, I've got silly putty around here. If you stretch silly putty slowly, you've all played with silly putty. You can stretch it slowly and it'll form a nice long string. That's like if you're dealing with the asthenosphere, a partially molten kind of crust. But if you were to pull the silly putty apart quickly, you'll break it brittly and it'll form just like a one plane where it breaks apart. That's how rocks break when they're solidified completely. They're brittle and they just break along a fracture. And if that fracture actually moves, it slips, then you generate an earthquake. Okay. Here we go. So another inside look at a mid-ocean ridge. Here's the seafloor, the ridge forming. Here's the V-shaped notch where the magmas are rising up and feeding the lavas, the basaltic lavas that are forming along the axis of the ridge. These tilted blocks are like the dominoes I was trying to describe. That form from these faults as the plates are pulling apart at that point. Right along where these lavas are erupting, you're getting pilobasalts. So the pilobasalts only form on the seafloor. They're not going to form underground ever, because you're not going to get that pillow shape unless they're erupted into water. Beneath that, you have a bunch of basaltic dikes that feed the mid-ocean ridge. And so that's what this is representing, is all the dikes that are coming up from this magma chamber. So it's probably not a single place. It's probably multiple places where magma is finding its way up through the basaltic crust. Deeper down, it's not volcanic rock, it is the plutonic equivalent. So the chemical equivalent of basalt is a gabbro. They can look very dark, but they have a lot of feldspar, plagioclase feldspar, which is what this white material is. That just means that those basalts never made it to the surface. Those were ones that cooled underground. The ones that were set free were either turned into a dike or came up as a pillow basalt. And then below, the Moho is right here. So at the base of where these gabbros are, the Moho is, remember, the division between the crust and the mantle. That's the name of that distinction. And it was discovered because of the density differences between the mantle and the crust. So that means the density increases quite a bit here, going from crust to the mantle. I think it goes from about 3 to about 3.3 grams per cubic centimeters there. And the rock is different. So instead you get an ultramafic rock. This is called a peridotite. Peridot, it's mostly olivine crystals. It doesn't always look like that. Sometimes it might just be a completely black rock or a brownish bronzy rock, but they're definitely ultramafic. So these rocks are mafic. Any mantle rocks are ultramafic. So even less silica, even more iron, magnesium, chromium, other metals. Okay. Continental rifts are places on the continents, as the name suggests, where the crust has started to spread. This doesn't mean it's a plate boundary yet, but it could likely become a plate boundary. In the case of East Africa, so you guys are probably familiar with the East African rifts, maybe from anthropology, because some of the earliest hominids were found in these rifts in Ethiopia. This was a triad. There were three places where three different plates, the African plate, the Indian plate, and the Arabian plate, all come together right about here in this triangle. It's called a triple point, where the triple being from three plates. So this triple point is where those three plates meet. Oftentimes there are two that succeed in becoming actual rifts and the initial stages of building an ocean basin. So the Red Sea is called the Red Sea Rift, and there's another rift in the Gulf of Aden or Aden. I'm not sure how you're supposed to say that. Probably Aden. Okay, so these two are tiny. They're seas right now, but they're going to become oceans over geologic time. Those are going to open up and separate. They're going to push Africa away from the Arabian plate, and the Indian and the African plate will be pushed away from the Arabian plate at that point. This is considered a failed rift. There's still volcanism there. It's still an active place where there are volcanoes. These red triangles are actually marking active volcanoes. Oldenyo Lengai is a really cool volcano that I'll probably show you when we get to plutonic rocks. It's weird. I'll show you why it's weird. Okay, so what's happening in that failed rift that hasn't opened up to become a sea? What does it look like? It looks kind of like this. There's an area that is stretched. You see the crust is thin. that means that the mantle has been decompressed again. So anywhere you get thin crust, you're decompressing the mantle a little bit, and you start to melt it. And so there are partial melts of mantle that are basalts. There are always basalts when you get a partial melt of the mantle. So you melt it a little bit, and it's sending basaltic rocks, basaltic magmas up toward the surface. Some of them erupt as basalts, as basaltic lavas, but others, their chemistry changes as they pass through the continental crust. And so you can actually get you can get both mafic and felsic rocks erupting in continental rifts for that reason. They give it a name called bimodal volcanism. You don't have to remember that. It just means that you've got two kinds. You've got basalt and you've got rhyolite. Felsic, mafic. And you also have a series of normal faults. These are these stretching faults that create space. So the faults would happen on one side of each of these ridges. So each time there's a fault, it drops down a block of crust that forms a basin and uplifts a ridge. So you're seeing this ridge basin sequence across that space. This is just what it looks like if you've driven across Nevada and Utah. Even like Death Valley, the Mojave Desert, that's where this stretching starts in North America. So we have our own continental rift. We call it the Basin and Range. It's an appropriate name. It's a geological term for it, of course, but that's what it's referring to, is this series of basins and ranges that form where the crust is stretching. Again, it's not a plate boundary. In the case of North America, the San Andreas Fault, there's evidence that the San Andreas Fault stresses might be migrating to the east of the Sierra Nevada, and they could be migrating toward the basin and range. So in geologic time, this could open up. This would make California its own kind of island, I suppose, at some point. Yeah, what else do I want to say here? Okay. I'll tell you more about that in a minute. We've had a bunch of earthquakes in the Eastern Sierra recently here that indicate that those stresses are moving. But I want you to realize that this is a related process on the continents, although these are not plate boundaries yet, okay? So East Africa and the Basin and Range, not plate boundaries. They are near plate boundaries. They're just places where those sorts of stresses are being applied to the continents. All right. Okay, so here's another look. Here's the Red Sea, Gulf of Aden. Here's the East African rifts. Lake Victoria is in there. Bunch of different rifts. So all these lakes fill up rift valleys. And what it would look like is, like, if you start off with a hunk of crust that just like all the layers, we've got lithospheric crust here, lithospheric mantle and crust there. You probably start with processes happening in the mantle. So there's maybe upwelling of hot mantle and maybe some melts that are coming up to get this process started. So you start the upwelling, you start spreading the crust, erupting lavas. You spread it some more and some more and some more. And if it's going fast enough, or the process is continuous enough, you eventually open up a valley that's low enough that oftentimes if there's an adjacent ocean, that water rushes in to fill that valley because it's forming such a low point. Basically, it'll come down to sea level at some point and let the ocean in. And so it forms a small sea. So this stage might be where one of these rift lakes is forming right now. And I would say that this is what like the Red Sea or the Gulf of Aden looks like. It's a small ocean basin. It's not a fully developed, mature ocean floor there. Okay. So this whole process has been really important in moving the plates around, right? This is the process that broke up Pangaea. This is what separated Africa from South America and Europe from North America. So important. I feel like I've already explained this, so I think I'll move on. I just want you to realize it's thin crust. It becomes oceanic crust where you've got a basaltic floor to it. Once that happens, once a sea forms, those are the beginnings of opening up an ocean. Okay, so that was it for divergent plate boundaries. Are there any questions about divergent plate boundaries before we start convergent plate boundaries? You've been very quiet today. Or I've been very talky. Now's your chance. Okay. All right, so, let me just point out, I'm going to talk about two different kinds of plate boundary, convergent plate boundaries. I'm going to talk about different kinds of subduction zones. There are three kinds of subduction zones, basically, and there are different kinds of continental collisions. So a subduction zone forms where oceanic crust is involved. So one of the plates in these cases is an oceanic plate. Continental collisions are where two continents collide. So like the Himalaya. So this would be like Chile or the Japanese arc of volcanoes, and this would be like the Himalaya in Tibet. We'll get to all of them. Okay. We'll start with, so these are the basic three kinds laid out. Here's an ocean-continent collision. Here's an ocean-ocean collision, and here's a continent-continent collision. Meaning these are two oceanic plates. This is an oceanic plate and a continental plate. And these are two continental plates that are colliding. All right, so some examples of where you've got an ocean that's diving down beneath the edge of the continent. Chile, the Aleutian Islands, actually, that's a bad example. I'm gonna move that down here to Japan. The Aleutian Islands are, oops, I missed, that's where the N came from. The Japanese islands and the Aleutian Islands are great examples. Like this looks like Japan because there's a chain of volcanoes very near the continent, but it's a small ocean, basically a sea between that island. We call them island arcs or volcanic arcs because on a sphere, a line turns into an arcuate shape. So a line of subduction, if you're sending an oceanic plate down like this, well, on a globe, it's going to end up looking like a curve. So we call them volcanic arcs, oceanic arcs. And the volcanoes that are in Japan, the Kuril Islands, the Kamchatka Peninsula in eastern Russia, a bunch in the Southwest Pacific, all of those are places where oceanic crust that is subducted beneath another piece of oceanic crust. Now, you should know something about the oceanic crust in this situation. So tell me about the oceanic crust that the volcanic arc forms on. What are the properties of the basaltic crust there? Does anyone have want to volunteer something? Okay, you're keeping an eye out for the chat for me, aren't you?
I am.
Awesome.
There haven't been any questions.
Thank you. Again, really quiet. Okay, so what if I ask the question, or you're gonna volunteer something?
Sorry, what was the question again?
I'm asking you about tell me about the properties, the physical properties of the basaltic crust that forms the overriding plate, the one with the volcanic arc.
Well, the overriding plate is going to be less dense,
Yes.
and so
So
that
tell me about the
allows.
age of this crust then.
It's also
compared to the-
younger. Typically, the denser plate subducting is the older one,
Oh,
and
wait,
it's also cooler.
Yes, that's right. Wait, I had it backwards in my head for a second. Yeah.
Yeah, the
So
subducting plate's older.
this is older, and the way that you know that is because it's denser. So it has become denser than this oceanic crust. So this oceanic crust must be younger and more buoyant than this downgoing plate. So the one that loses in the subduction zone, the plate that loses is the denser, older crust. You're right. So it's older, colder, and denser. And this is younger, more buoyant, and less dense crust. That's a great exam question. Just FYI, if you're taking notes. Okay, so that's that example. Places where you've got an ocean continent collision zone, for some reason, I'm not, Cascadia, the Cascade range. So right here where the Juan de Fuca plate, the oceanic plate, is subducting beneath Northern California, Oregon, Washington, that's this sort of situation where it's an ocean plate that is old and cold and dense, but that's being subducted beneath the continents. But the continents are always going to win versus the oceanic crust, because the continents are granitic. They're much less dense. They're like 2.8 grams per cubic centimeter instead of 3 grams per cubic centimeter. It doesn't sound like a lot, but it makes a big difference. What else do you see forming right here and right here? That's an important part of this that you will see in your lab. I'm pointing to the trench. So as the oceanic plate is subducted, it actually bends that ocean crust. So actually, just before it dives down beneath the continent, there's a little bulge. It bulges upward. So it flexes upward before it bends down. And as it bends down, it's pulling the crust with it, and it forms a deep ocean trench. So in the case of the Japanese islands, right, and the Marianas, which are to the south on a map on the globe, one of the deepest places on Earth is in one of these trenches. It's in the Marianas Trench, where one of these subduction zones is happening. So it's right at the plate boundary. Okay. Did I mention everything? I think I did. So notice, okay, here's another thing I want you to notice. Notice that the subducting plate dives down, that melting doesn't happen until you get inboard of that subduction zone. So the plates actually contact each other right here. But the volcanoes don't form until, let's say, 100 kilometers or 150 kilometers, something like that, 200 kilometers from that margin between the two plates. So why? What's happening, and this, I'm going to go into more detail than I expect from you guys, but what I do expect you to know, that it is not the subducting plate that melts. The oceanic crust of that subducting plate does not melt. What melts is the mantle. It's the mantle that's above the subducting plate. that becomes partially molten and sends up basaltic magmas. Why that happens is this. When you're subducting this crust, what are you bringing with it? You're bringing all of those rocks in that cross section of oceanic crust. You're taking the gabbros and the basalts and the pillow basalts and those sheeted dikes and the peridotite, the mantle rocks. You're taking all of that with it. You're also taking the seafloor sediments and sediments shed from the continent that make their way to the trench. And you're taking probably some of the water from the ocean that fills those sediments. So there's a lot of gunk going down this trench. And that's got water in it. The oceanic crust that's going down has some minerals in it that contain structural water. It's a hydroxyl group in the mineral formula. It's not actual liquid water. But as you metamorphose the rocks, because you're sending them very deep, you're heating them up, you're applying a lot of pressure. It's mostly the heat as they get hotter as they go down with just the heat from the interior of the earth. As you go down, you're starting to metamorphose those minerals and they change. And any minerals, like it could be a clay mineral from the sediments or a biotite mica or an amphibole mineral or something like that, they transform and they give off water from the crystal structure. And that water, it's buoyant compared to the rocks that surround it. So the water rises up and it enters the mantle that's above that subducting plate. And when the water from that subducting plate rises up and enters the mantle, it actually lowers the melting temperature of the mantle rocks and they can start to melt. So you're actually changing you're changing the pressure, and not the pressure, but the temperature. You're not changing anything about the pressure or temperature that the mantle rocks are at. It's not like you're taking the pressure off and decompressing them and letting them melt. That's not happening. It's literally the water that enters the peridotites, the whatever mantle type rock is there, that starts to melt because of the addition of the water. It forms basalts, just like at the mid-ocean ridge. That mantle forms basaltic melts, but we don't necessarily get basalts on the surface or coming out of these volcanoes because they have to go through a big, like many tens of kilometers of continental crust first. And during that time, they can incorporate pieces of continental crust. They can melt some of the continental crust and combine it with the basalts. And it's changing the chemistry of the magmas as they rise up through the continents. And so what comes out of the volcanoes is more andesitic. It's an andesite, like the Andes Mountains. Oh, I should have added the Andes, or that's Chile. I'll add the Andes there. So it's andesite is named for the Andes. It's an intermediate composition. It's neither felsic nor mafic. It's intermediate. So it's got the properties, instead of 70% silica or 50% silica, it's more like 60% silica. And it's got more of the dark minerals that have the iron and magnesium than you would find in a granite. It's literally intermediate. So that's why that it's intermediate, is because these basalts have to pass through the continent and before they can be erupted. And remember, once you've got a mountain belt built up, that crust is even thicker and thicker because of isostasy. The isostatic balance is going to mean that beneath any volcano, any mountain range, you're going to have thicker crust, thicker lithosphere. The same process is happening in the ocean-ocean collision. Same idea about metamorphism of the subducting plate, bringing down water. The water rises up into the mantle. And at first, it would probably erupt basalts. But over time, once you develop islands there, then you can start, then the chemistry of the melt starts changing and you get more andesitic material. Okay, I've talked this to death right now. All right, continent-continent collisions like the Himalaya. Imagine this is the Indian plate, because it was, or is. It's the Indian plate being pushed underneath the Asian plate, except it doesn't look like this. This is way too steep of a subduction. The angle that the Indian crust is subducting beneath Asia is more like 10 degrees. It's more like this. It is very flat, and the crust is very thick because of that in the Himalayas and Tibet, because it's like two continents on top of one another. It doesn't dive down because the crust is simply too buoyant. So this is, I think, exaggerated to make the point about subduction, or one continent moving beneath the other. So where the Himalaya are concerned, the crust is extremely thick. It's 80 kilometers thick beneath the Himalayas, just the crust, not the lithosphere. And what else do I want to say? And in that case, there's a plateau behind it that in part arises because the Indian continent is buried underneath it somewhere. Okay, the Ring of Fire. Here we go. Why is it the Ring of Fire? Why is it called that? Because of all the subduction zones, and these are ocean continent subduction zones, or ocean-ocean subduction zones. So not any continental collisions, but ocean-ocean collisions here, Japan, here with the Aleutians, places in here, like right there in Malaysia, near the New Guinea, Papua New Guinea, in Tonga, the Tonga Kermadec Trench that goes almost to New Zealand. There are some other smaller plates down in here too. There are a bunch of smaller plates in here that make the tectonics of this region insanely complex. So I like to stick to the simple examples. These volcanoes, in addition to having like a chain of volcanoes forming everywhere you've got one of these subduction zones, you're also going to get earthquakes. So what do I want to show you here? I guess just one example of oceanic crust beneath continental crust. This is the South American example. It's the Nazca plate that is subducting beneath South America. It's obviously newer crust here, quite a bit denser there, but it's, again, oceanic crust versus a continental crust. So the oceanic crust is going to subduct. It subducts at different angles. There are places where this subducts really steeply, and you get typical volcanoes that you would find like in the Cascades, but there are also places where it subducts more shallowly. And there's actually, it's called the Altiplano, the high plain. There's a plateau here similar to the Tibetan plateau, just not as big, that forms because of some shallow subduction there. And so some weird stuff that's probably right here where there's an old ridge or an old fracture zone that is being subducted. So the crust is a little bit different in that position. But this is what you need. Oh, and the Cocos plate, of course, between from Mexico and through Central America. So all the volcanoes like in Nicaragua, Guatemala, Costa Rica, Mexico, all of those volcanoes are forming from subduction of the Cocos plate. the Cocos Plate, so all this line of volcanoes and the line of subduction zone there, it changes. And we actually have, this is a mid-ocean ridge, right? That goes right up between Baja and mainland Mexico. So in the Gulf of California, it's opening up like a small sea. It's opening up to be an ocean. It will become an ocean at some point. Where it reaches the continent at Southern California, it becomes the San Andreas Fault. So then we have a transform fault boundary, and then another subduction zone up here where the Juan de Fuca plate is subducting beneath North America, and we get the Cascade Range, like Mount St. Helens, Mount Rainier, Mount Hood in your lab. Okay. The transform and this divergent plate boundary, do you remember the directions, the plate motions I showed you that had the arrows going every which way? Maybe you'll recall that the Pacific plate was, its overall motion was to the northwest, and it had a pretty long arrow, which means it's going pretty fast. It was like maybe 11, 12 centimeters per year. And centimeters per year, or sorry, millimeters per year work out to kilometers per millions of years. So you just do the math. So millimeters a year that we can measure on our time scale becomes kilometers per millions of years. So this plate is going to move 12 kilometers in a million years, or 12 millimeters, 1.2 centimeters. So like this. And North America had a smaller arrow that was moving sort of the same direction, but kind of west. And overall, the stresses mean that there's a transform. There's mostly horizontal motion at that place. So the plate is kind of moving in the same direction as the San Andreas Fault to get that transform motion there. Okay, I'm not talking about that right now. I'm talking about subduction zone. So let's go back there. So this lays out what I've already said, but this is a good place to come back if you need kind of a written explanation of what I said. I said the subducting plates do not melt, right? The water that comes down with it, and the water, the structural water and the minerals in the oceanic crust will transform from metamorphism. So you get metamorphic reactions that dehydrate hydrous minerals. So any minerals that have water in them, they lose their water. That's what dehydration means. And what's melted it's the hydrated mantle. This is calling it a asthenosphere. It's just the upper mantle. The water enters there, it lowers that melting temperature, and it's the mantle that melts. That sends up basalts that then, once they enter the continental crust, their chemistry is changing. Don't worry about this right now. That'll save this for metamorphism. Look at mostly these boxes here. So we've got the metamorphic reactions, we've got the water entering the mantle, lowering the melting temperature, feeding those volcanoes. We have the trench that's forming right at the collision zone between the two plates. And these stars, these little explosion looking stars, are earthquakes. So this is showing you earthquakes that are shallow, but they get progressively deeper. Where are those earthquakes happening? It shows it kind of like on the line between the two plates, but what's causing the earthquakes? Does anyone want to hazard a guess? Okay, it is the oceanic crust that's subducting. It's stretching and breaking where it's bending down to go down in the subduction zone. And there are also metamorphic reactions that can change the density of the minerals and the density of the overall rock. That happens deeper down. But what I'm saying is it's the brittle plate, it's the oceanic plate that is subducting, that is brittle, behaving brittly, and that's breaking to form those earthquakes. And so when we look at, I'm just going to skip forward to not that one, to this one. If I skip forward to this, everywhere you see the yellow and green earthquakes, those are those deep earthquakes. And you can even see which way the plate bends. The plate is pushing this way and subducting beneath that ocean plate in this direction, because the shallow earthquakes are on this side. They get deeper that direction. So if I were to plot, wait a minute, where was I? If I were to plot those here, so if you plot an earthquake from deep down on the subduction zone, if you plot the epicenter on the surface, you would plot it up here. That's the epicenter. So the deeper earthquakes plot further inboard, inland, if there's a continental collision, ocean continent. So you're going to see the shallow earthquakes near the trench, and you're going to see the deep earthquakes furthest away from the trench, and maybe underneath the arc. Okay, I guess that's what I want to leave you with, is that with this idea with the depth. We'll talk about the magnitude of the earthquakes next time. You know what? Since it's only 3 after, let me just, I just want to get to this little video since we've been talking about this. Okay, I'll go back to this one next. I want to show you this one. So it's another video showing a subduction zone. So this is an oceanic plate subducting beneath the continent. So here are here's the bending and breaking of that oceanic plate as it goes down. It's stretching and forming these cracks. Do you see how it's dragging down material as it goes? I'll keep playing it. It's dragging sediments from the trench, and it's taking the oceanic plate. It's dragging and pulling that material down. And it's not until, I'll do it one more time. It's not until you get deep down here that enough water has been released from those metamorphic reactions to lower the melting temperature of the mantle and to generate those melts. Now this is going way faster than it otherwise would. These magmas are rising really quickly, but you got the idea. They're feeding these volcanoes. I like this animation. I think it's really cool. It's the best one that I've seen. Tanya Atwater, who is at UC Santa Barbara, makes these. And she's a National Academy of Sciences member. So that's the ultimate prestigious position you can have as a scientist, is to become a member of the National Academy. Okay. You usually get there by some like big discovery or just major innovation in your research sort of thing. I'm going to stop the lecture there. I'm happy to answer any questions about what we covered today. We're not quite done with subduction zones. We have a few more. We need to go into the continental collisions first. But I'll leave the slides up so you can ask about the slides. I'm happy to take questions about that. Happy to take, sorry, oops, I'm trying to leave it on the right side. I'm going to close that. Save. And okay. So I'll take any questions. Feel free to stick around and ask questions. I just realized I'm not plugged in here. Ask questions about the labs. The Google Earth lab, I can try again so I can demonstrate some things. But if you haven't gotten it going, stick around and let's try to get Google Earth working on your computer together. Okay? So, but if you're done, if you're good to go, you're happy downloading that material and working on the lab yourself, feel free to sign off, and I'll see you Tuesday or maybe tomorrow. Come back tomorrow 11 to 1 if you have questions, if you're working on your lab. Please finish 5A this week, because I want you to work on 5B starting maybe over the weekend, okay? 5B is going to take more thought. Now I'm done.
Thank you.
Bye.
Thank you, Mary.
Bye. See ya.
Bye.
Goodbye.
See ya.
Thank you.
You're welcome.
I just have one quick question about the lab that's due this week to relate the relative dating one.
Sure.
It's due at midnight tomorrow, right?
If you need a little bit more time, you can have it.
Okay.
If you need the weekend, okay? But do try to finish that so that you can get going on the Google lab, because I mean, even if you get like most of it done, like if you can get like 80% of the last question done, you'll be fine. Just try to make sure you mention everything that's in the list that you're supposed to mention in that last question. But I'd really like you to get Google Earth going and to do 5A over the weekend as well. It shouldn't take that long. It's mostly just, if you've used Google Earth before, you're fine. You'll be fine. If you haven't, there's a little bit of a learning curve, but it's pretty easy to use.
Okay.
Okay.
Yeah.
I mean, if you want to try to install it now, I can help you.
Oh no, I think I already have it installed. I mean,
Okay.
it seems to be working.
Oh, good. And you got the layers? You opened the layers within it?
I didn't open the layers.
Okay, so make sure you download the Geologic Map of California and the topography layers, the KML and KMZ files that are right next to the worksheets in the lab. They're right here, that you need to add in to do that lab. So as long as you understand it's these ones, Map of California and the topo. Add those. You're going to open them from within Google Earth. But if you got Google Earth installed, you'll probably be fine. Just follow the instructions.
Okay.
Okay.
Thank you.
Welcome.
Professor?
Yeah.
I had a question about Lab 5A.
Is this
Just one of the
Caitlin?
questions.
This is Caitlin I'm talking to?
Oh, yeah.
Okay. Cool. Okay, so which question do you have a question about?
It was number 10. It says, what is visible in the Google Earth image where the topographic map contour lines are brown rather than blue? I figured out how to do it, but I can't really tell what it's supposed to be.
Could you share your screen? Do you have it right there?
Yes. Hold on.
Because I'd rather you point it out, because I'm not looking at it right now, although I can try to.
Yeah, okay, so I realized that it says like you can like switch the like so it's a little more opaque, but the question is like what do you see when the lines are more brown than blue?
It sounds like those are contour lines. Is that what you're looking at? Is a contour line?
Well, the question is asking what is visible when the contour lines are brown.
Okay, show me.
So, I mean, I can slide the bar back, and then it looks like it's brown.
I'm not seeing anything right now.
Am I sharing Google?
Oh, now I see. Now I see. Okay.
Oh, okay.
Sorry, it might have been hidden, or I don't know what was going on. Now I can see. Okay.
So cool. I'm sliding the bar back and forth. I can tell it's blue right here, and then it turns more brown. But I don't really understand what that's
Zoom in for me.
I mean, I guess you could see the features of the mountain once
those are just the contours.
Well, yeah, that's what it's asking. It says so you can see, because there's basically the question just asking like, what do you see when the contour lines are brown? It's just a contour line.
It says when the contour lines are brown, or when the lines are brown.
When the contour lines are brown, it says what is visible in the image.
It's elevation above sea level.
Oh, okay.
Or now I'm confused by the question. Let me go just look at it. And
Yeah,
and
that's what I was thinking. It just kind of confused me for a second.
well, you know, this is the first time I've tried this lab with anyone, so there could be questions that could be improved in their wording. Let me just look. So this 10, right?
Yeah.
Okay, you can adjust the opacity of a layer so you can see the aerial image. Okay, so just click on the screen. It's just I think unless it's talking about the now I need to go through this step and just see. Oh, okay, wait, it's talking about a glacier next to it. Okay, so the glacier has blue lines. Maybe I shouldn't have included the word contour in that. I just answer it like this. Answer that their contour lines are brown and that they show elevation above sea level, and that there's brown shading on mountains.
Okay.
That ought to cover everything.
Okay. All right. Thank you.
You're welcome.
Bye.
Bye.